While we can easily determine if g of n is not order f of n, we probably want to know which complexity class g of n is actually in. For that, we can use big O and omega as follows. Let's consider this limit. We'll assume the limit exists to give us a possibility of answering it. There are three important cases. The limit is 0, the limit is some positive real number k, and the limit is infinity. Now, suppose the limit is some positive real number k. Then our theorem tells us absolutely nothing. Remember, to use an if something, then something, you have to have the antecedent. In other words, we have to know that g of n is order f of n. So we need another approach. And for that, remember, definitions are the whole of mathematics. All else is commentary. Since the limit as n goes to infinity of our quotient is k, then by definition, for any epsilon greater than 0, the difference between that quotient and k can be made smaller than epsilon for all sufficiently large n. So that means this quotient is wedged between k minus epsilon and k plus epsilon. Now, since we're assuming k is positive and we only care about small values of epsilon, then there are real values, c prime, which are less than k minus epsilon, and c star, which are greater than k plus epsilon. And so this quotient is wedged in between these two positive values. And so we know that for all sufficiently large n, g of n is going to be somewhere between a multiple of fn and a different multiple of f of n. Now, since g of n is less than c star of f of n, then g of n is big O of f of n. And since gn is greater than some multiple of f of n, we also know that g of n is omega of f of n. And so that means g of n is in both big O of f of n and omega of f of n, which means that g of n is order f of n. Note that this is the converse of our theorem, and so we have proved. Suppose the limit of our quotient is k, where k is some positive real number that's not 0 or infinity. Then g of n is order f of n. So, for example, we might want to show that some function is order n cubed. So we'll go ahead and find the limit of that quotient. Now, while we could use L'Hopital's rule, we have a copay for going to the L'Hopital. I'm realizing that joke only makes sense if you're in the United States, since for-profit healthcare is an American aberration. But still, we want to avoid L'Hopital visits if we can, so let's do some algebra. And in this case, since we have a quotient, we can split the numerator and simplify each of our terms. And as n goes to infinity, this limit goes to 1. And since the limit is a positive real number, this function is order n cubed. So a useful thing to do when you're trying to learn new material is to prove it again. To show that n cubed minus log n plus root n is order n cubed, we need to show that it's both big O of n cubed and omega of n cubed. And note that for sufficiently large n is greater than log n, and n is greater than square root of n. And what this means is that this function, we can make it bigger by not subtracting log n, and we can make it bigger by replacing root n with n, and we can make it bigger by multiplying n by n squared, and so our function is big O of n cubed. And by the same reasoning, we can make our function smaller by not adding square root of n. We can make our function smaller by subtracting more. We can further increase that subtraction, but we have to be careful here because we don't want it to vanish completely. and that tells us that our function is omega of n cubed. And since our function is big O of n cubed and omega of n cubed, then it's in both, and so it's order n cubed. What if our quotient is 0 or infinity? Suppose the limit is 0. Then if the limit is 0, then for any epsilon greater than 0, then for all sufficiently large n, we have the quotient smaller than epsilon. And again, if we're assuming that f and g are complexity functions, they're positive, so we don't need that absolute value, and we can multiply across without changing the direction of the inequalities. Since we're assuming epsilon is small, it's going to be less than 1, and so g of n is less than f of n, so g of n is big O of f of n. Could g of n be omega of f of n? This would require that for any c, then for all sufficiently large n, g of n is greater than c f of n. But for all epsilon and all sufficiently large n, g of n is less than epsilon, and so that puts g of n sandwiched between cf of n and epsilon f of n. Or our quotient is less than epsilon, but it's greater than or equal to c, which is any c that we want, which is impossible. So g of n can't be omega of f of n. And this means that if the limit of our quotient is 0, then g of n is not order f of n. And by a similar argument, we could show that if the quotient is infinity, then g of n is not order f of n. So let's show that n to the 1000 and e to the n do not have the same order. Now, we already did this, but again, let's prove it again. So we can take a look at our quotient. We can apply L'Hopital's rule, but note that if we keep differentiating numerator and denominator, the polynomial eventually reduces to a constant, while e to the n stays e to the n. And so we'll get, and the limit will be 0. And so n to the 1000 is big O of e to the n, but it's not omega of e to the n, so they have different orders.